Okay, let's unpack this. We talk a lot about happiness, right? It's arguably the universal human quest.
It really is. Everyone's chasing it, in one way or another.
That feeling of a good mood, joy, exhilaration, bliss. We intuitively understand what it is, and we chase after it in countless ways throughout our lives. But have you ever really stopped to consider what's actually happening inside your brain when you experience that feeling? What are the intricate mechanisms firing?
Yeah, what's going on under the hood, so to speak?
Exactly. Today, we're going far beyond just the intuitive understanding of happiness. We're embarking on a deep dive into the complex neurobiological underpinnings of happiness motivation.
And even how our capacity for joy can surprisingly change across our entire lifespan. That part's fascinating.
It really is. We've compiled a truly fantastic stack of scientific articles and cutting-edge research to guide us, offering you, our listener, a direct shortcut to being truly well-informed on the brain's own blueprint for bliss.
That's absolutely right. Our mission today is to emphasize that happiness isn't merely some abstract cognitive construct, something we just think about or define for ourselves. It's an immediate, visceral, emotional experience rooted deeply in our biology, a symphony of neurochemicals and neural circuits firing in precise ways.
A symphony, I like that.
We're going to extract the most important nuggets of knowledge from the material you've shared, connect the dots between findings that might seem disparate at first glance. Our goal is to reveal some truly surprising insights into what makes us feel good from a purely brain-based perspective.
Okay.
Our journey will take us from the key neurotransmitters and specific brain regions involved to understanding the different fascinating types of happiness and how they evolve as we navigate through life. It's a profound look at the very core of our well-being.
All right, let's dive in. Let's kick things off with the familiar players, shall we? When we think about happy chemicals in the brain, a few names immediately jump to mind.
The usual suspects.
Exactly. We're talking about dopamine, serotonin, and oxytocin. For a long time, and even in common conversation today, dopamine is often singled out as that hormone associated with happiness, the one that delivers that feeling of reward or pleasure.
The feel-good chemical, yeah.
Right. And serotonin, well, that's generally understood as the chemical that regulates our mood. We hear about it constantly in discussions around mental health, frequently linked to feelings of well-being, or conversely, depression.
Often mentioned with SSRIs and things like that.
Exactly. But as with most things in the brain, there's so much more to their story than just these simple, often oversimplified descriptions.
Oh, definitely. What's truly fascinating here is how these chemicals don't work in isolation. They perform a complex, orchestrated dance, especially in specific emotional contexts. Take something as universally powerful as physical attraction, for instance. When you're intensely drawn to someone, it's not just one chemical doing all the heavy lifting. Our sources indicate there's a dynamic interplay. You see an activation of dopamine, a significant increase in serotonin, and a surge in the production of oxytocin.
So all three are involved in that initial spark.
Absolutely. Oxytocin, often affectionately dubbed the love hormone or bonding hormone, plays a particularly crucial role here. It actively reduces pain perception and increases the emotional connection we have with the other.
Ah, so it helps build that closeness.
Think of it as your brain's natural social glue, smoothing over potential anxieties and deepening your sense of closeness. And then there's this incredible, almost paradoxical effect, the temporary disconnecting of the amygdala.
Wait, disconnecting the amygdala, the fear center.
Exactly. Now, the amygdala is a small, almond-shaped region deep within your brain, essentially your brain's alarm system. It's highly active when processing negative emotions like fear, danger, or anxiety. Its temporary deactivation in the context of intense attraction, or that feeling we call a crush, means your brain is essentially dampening those alarm bells, lowering your guard,
Wow.
and allowing you to fully immerse yourself in that positive connection without the usual inhibitions or self-protective instincts. It's your brain creating a unique, temporary window for intense bonding.
That makes so much sense. It explains that sort of fearless feeling you get early on.
It really does. And understanding these intricate functions, this neurochemical orchestration of powerful emotional states, isn't just an academic exercise.
Yep.
It offers profound insights into human behavior. The sources suggest it can actually help us prevent many interpersonal conflicts by providing deeper insight into the functioning of our brain and human relations.
Huh.
Well, it suggests that our internal neurochemistry heavily influences how we perceive and react to others, Ultimately, how we interpret these complex internal states and how we understand ourselves and the world around us eventually determines if we made a good choice in our interactions and relationships. It's a powerful reminder of how much our biology shapes our social world.
That's incredibly insightful. The idea that our brain temporarily disarms its own fear response to allow for connection helps explain a lot about the intensity of new love or attraction. But here's where it gets really interesting, because while dopamine often gets all the attention for reward and pleasure, and serotonin is often painted as this simple, happy chemical, the reality, particularly with serotonin, is far more complex and, frankly, a bit mysterious.
Ah, yes, serotonin. It's not so simple.
Not at all. Our sources reveal that while it's clearly involved in regulating mood, its role isn't always straightforward or uniformly positive. For instance, dysfunctional interactions between the serotonin system and the dopamine system, particularly in the prefrontal cortex.
That's our planning and decision-making hub.
Right. Those interactions have been linked to aggression. In fact, a serotonin hypofunction, meaning lower than normal serotonin activity, may represent a specific biochemical trait that actually predisposes individuals to aggression.
So, low serotonin isn't just about sadness, it could link to aggression too.
Exactly. So it's definitely not simply a matter of more serotonin equals more happiness or less serotonin equals more sadness. There's a subtle and powerful dynamic at play.
Precisely. The research consistently points to what they call the ambivalent and even mysterious nature of serotonin, or 5-HT, as it's known chemically. While its widespread involvement in both rewarding and aversive processing, meaning both positive and negative experiences, as well as mood and higher cognitive functions like consciousness or self-reflection, is completely undisputed.
Okay.
Its precise contribution has long been controversial among neuroscientists.
Controversial how?
Think about it. Early theories were actually quite contradictory. Some position 5-HT as a behavioral inhibitor in an aversive context.
Like a break.
Exactly. This means it was thought to act like a brake, helping you stop behaviors that might lead to bad outcomes or negative experiences. It's like your brain telling you, hey, maybe don't do that. It didn't work out well last time.
Makes sense.
But then other research simultaneously suggested its strong influence on reward processing, implying it was part of the accelerator for good feelings, encouraging you to pursue things that felt pleasurable.
So a brake and an accelerator, that sounds confusing.
It absolutely does. This seemingly opposing dual role has fueled a long-standing, often heated debate among neuroscientists. It's a perfect example of how our understanding of brain chemistry isn't about simple one-to-one functions, but rather about complex, nuanced interactions that evolve as research methods become more sophisticated. It challenges us to look beyond simplistic headlines.
So with all this complexity, what does this actually mean for us? When we talk about feeling good, are all good feelings truly the same experience in the brain?
That's the million-dollar question, isn't it? And neuroscientists would tell you definitively no.
No.
They've drawn a critical distinction in the brain's reward systems between what they call liking and wanting.
Liking versus wanting.
Right. Think about it. The very word happiness itself is incredibly broad. The Oxford English Dictionary defines it as good fortune or luck, or the state of pleasurable content of mind.
Then you have synonyms like pleasure, joy, exhilaration, bliss, contentedness, delight, enjoyment, satisfaction. It's a huge spectrum.
A massive spectrum. But scientifically, those diverse feelings can actually stem from very different neural pathways within your brain, even though they all contribute to your overall sense of well-being.
Okay, so break that down for us. Liking versus wanting.
That's an excellent point to draw out. Let's break down the distinct neural mechanisms behind liking and wanting, because understanding this separation is key to grasping how our brains truly process reward and motivation. Wanting is defined as incentive behavior, or more simply, motivation. This is the drive, the urge, the craving to pursue something.
Go get it feeling.
Exactly. This powerful drive is largely orchestrated by a network of subcortical structures deep within the brain, often operating beneath our conscious awareness. Key players here include the nucleus accumbens, the lateral hypothalamus, and the ventral tegmental area.
The drive centers.
You got it. Think of these areas as your brain's primary go-get-it or drive centers, constantly pushing you forward to acquire resources, achieve goals, or seek out experiences. These structures are intimately linked to the mesolimbic dopamine system, which is all about guiding goal-directed behavior and creating that feeling of anticipation.
So dopamine is more about the wanting.
It's heavily involved in the wanting, yes. To vividly illustrate wanting, consider the famous brain stimulation reward, or BSR, experiments from the 1950s.
Oh, the rats pressing levers.
Those ones. In these groundbreaking studies, rats had electrodes surgically implanted into these subcortical areas, like the hypothalamus or the medial forebrain bundle. When given access to a lever that would deliver a tiny electrical pulse to these areas, the rats would continuously self-stimulate, sometimes for days on end, pressing the lever hundreds or even thousands of times per hour, often foregoing food, water, or sleep.
Wow, thousands of times an hour.
It demonstrated an incredibly powerful positive reinforcement. They wanted that stimulation intensely. The drive to obtain it was overwhelming. But here's the crucial point, and it's a counterintuitive one.
Yeah?
While the animals clearly want the stimulation with immense intensity, it's not clear whether they are really gaining pleasurable feelings or positive emotions. Their behavior screams want, but the subjective liking isn't necessarily present.
So they're driven to do it, but not necessarily enjoying it. That's weird.
It is weird. On the flip side, liking is the subjective feeling of pleasure or pleasant feelings.
Yeah.
This is the actual enjoyment, the bliss, the contentment you experience.
The actual moment.
Precisely. This is associated with what neuroscientists call cortical hedonic hotspots. These are areas closer to the surface of the brain within the cerebral cortex and include regions like the orbitofrontal cortex, the insula, and the medial prefrontal cortex. These sophisticated cortical areas are responsible for encoding hedonic evaluations, which means they process and represent the anticipation, the actual moment-by-moment experience, and even the memory of pleasant stimuli. They're involved in that rich, conscious feeling of satisfaction.
Okay, so liking is more cortical, more conscious enjoyment.
Generally, yes. And the discrepancy between wanting and liking becomes starkly clear when we look at something as impactful as addictive behavior.
Right, you hear about this with addiction.
Exactly. Addicts often compulsively want drugs, driven by that powerful incentive motivation system, often described as a powerful craving. Yet, paradoxically, at the conscious level, they sometimes have negative emotions and do not like them anymore.
The craving is there, but the pleasure is gone.
Or significantly diminished, yes. The drive to pursue the drug is still there, sometimes overwhelmingly so, but the pleasure once associated with it might be absent, reduced, or even replaced by feelings of despair, shame, or physical discomfort. This highlights a fundamental separation in the brain. The urge to pursue something is distinct from the pleasure derived from having it, which is why addiction is so insidious.
The distinction really is fascinating. It's almost like our brain has a gas pedal for desire and a separate circuit for true enjoyment.
That's a great analogy.
And what's even more compelling is that this brain stimulation reward effect wasn't just observed in rats, it was also noted in humans, which really brings it home.
Oh, wow. And humans, too.
Yeah. Back in 1972, a pioneering researcher named Robert Heath conducted experiments where he set a stimulation electrode within the septal area of the human brain for patients with severe psychiatric conditions. And these patients reported a pleasant feeling. They described it as a general feeling of well-being, sometimes even a sexual arousal or euphoria when stimulated through this electrode.
Directly stimulating pleasure.
Apparently so. And when given access to a button, they repeatedly pressed it to stimulate their own brain, sometimes up to 1,500 times in just 3 hours, despite having other buttons for pain relief.
1,500 times. That's intense.
Isn't it? This strongly suggests that our brains include specific structures that can produce intense, pleasant feelings purely under electrical stimulation, a direct, almost raw way to tap into happiness.
Exactly. These human findings powerfully reinforce the idea that there are specific pleasure centers. And when we delve deeper into the brain, within the basal ganglia, a group of structures involved in movement control, motivation, and emotion, we find key subcortical pleasure centers, specifically the nucleus accumbens, often abbreviated as NX, and the ventral pallidum, VP.
MAC and VP.
Okay. These are not just theoretical constructs. Their roles are increasingly clear. Research shows that direct opioid stimulation, meaning activating the brain's natural opiate system in either the NAC or the VP, significantly enhanced liking response.
Liking response is like enjoyment.
Yes. For example, in studies with rats, this stimulation caused more positive or facial reactions to the taste of sucrose, like lip smacking or tongue protrusions, which are behavioral indicators of pleasure. But crucially, this opioid stimulation also simultaneously increased motivational wanting behavior, such as increased eating.
So it boosts both liking and wanting in those areas.
It seems so. These areas appear to be intimately involved in both the desire to consume and the pleasure derived from consuming, although perhaps with distinct emphasis. The NACIC seems to drive more of the wanting, while the VP appears critical for amplifying the liking.
Interesting distinction.
And a compelling, if tragic, human case really reinforces the ventral pallidum's distinct role in liking. There was a patient referred to as Mr. A, who suffered a selective bilateral lesion meaning damage on both sides of his globus pallidus, a structure closely connected to the ventral pallidum due to carbon monoxide poisoning. Prior to his injury, Mr. A was a heavy drug user, consuming significant amounts of alcohol daily. However, after the lesion, he reported something remarkable. He no longer experienced pleasure from drinking alcohol, despite the physical effects of intoxication remaining.
So he could still get drunk, but didn't enjoy it.
Exactly. He still wanted alcohol in the sense of craving and habit, but the subjective pleasure, the liking component, was completely gone.
Wow. That really pinpoints the VP's role in feeling pleasure.
It strongly suggests that the ventral pallidum is critically involved in mediating the actual conscious subjective experience of pleasure, reinforcing its specialized role as a key hedonic liking hotspot within this complex circuitry.
All right, so we've talked about the chemical conductors that initiate these feelings and the crucial distinction between wanting and liking. Now let's take a tour through the brain itself, guiding you through what scientists call hedonic hotspots, the key brain areas that literally light up with activity when we experience happiness.
Mapping the joy centers.
Exactly. It's important to remember, though, that while we've made incredible strides, the neuroscience of happiness is still in a relatively primitive stage compared to our understanding of, say, basic perception or motor control.
We're still learning a lot.
But thanks to remarkable advancements in brain imaging techniques like PET scans and fMRI, which allow us to see brain activity in real time, we've gained significant clarity on these pleasure-generating areas. How clear is this map for scientists right now? Are we talking about a fully detailed blueprint, or are they still filling in the blanks?
That's a perfect way to put it. We have a good sketch, maybe even a decent map, but not yet a complete, fully detailed blueprint. These brain imaging techniques have revealed a widespread network of areas activated during pleasure and positive emotions, collectively identified as hedonic hotspots. Let's start with the orbitofrontal cortex, OFC.
Okay, the OFC, where's that?
This area is located just above your eyes, right behind your forehead. It's absolutely crucial for representing the reward value of taste and odor.
So how good something tastes or smells.
Precisely. What's truly intriguing is that neurons in the OFC only respond to food when the animal is hungry. Once the animal is fed to satiety, meaning it's completely full and satisfied with that particular food, the neuronal responses to that specific food dramatically decrease.
Ah, so it adapts based on how much you need or want it.
Exactly. This phenomenon is known as sensory-specific satiety, and it perfectly illustrates the OFC isn't just registering the taste itself, it's registering how rewarding that taste is right now in your current state. It adapts.
That makes sense. Chocolate tastes better when you're craving it.
Exactly. And in humans, neuroimaging studies powerfully correlate OFC activation with subjective pleasantness across a diverse range of stimuli. For example, when subjects listened to their subject-selected music that evoked intensely pleasurable responses, the OFC lit up like a Christmas tree.
Music, too. Wow.
Music, yeah. The same was true for amphetamines, with OFC activation correlating directly with subjective ratings of a mind-racing euphoria. Even something as simple and universally appealing as chocolate activates the OFC, and its activity directly correlates with how pleasant the chocolate is rated by the individual.
So it's a general, how pleasant is this region?
It seems to be a key evaluator. What's more, there's a fascinating functional segregation within the OFC itself. The medial orbitofrontal cortex, located more towards the center, is predominantly related to positive emotion, responding to the pleasantness of taste, smell, or even a beautiful face. In contrast, the lateral orbitofrontal cortex, located more towards the side, is related to negative emotion, reflecting unpleasantness like monetary loss or painful touch.
So different parts for good and bad within the same area.
Seems like it. There's also a posterior-anterior distinction, meaning where something is located from back to front within the OFC. More complex or abstract reinforcers, such as the gain or loss of money, are represented more anteriorly, further towards the front.
Like financial rewards.
Right. Whereas simpler and concrete reinforcers, like a good taste or physical pain, are represented more posteriorly towards the back.
That's incredibly specific wiring.
It is. What this incredibly specialized wiring in the OFC tells us is that your brain doesn't just feel good or bad in a general sense. It has different dedicated circuits for processing how rewarding something is, from the simple pleasure of chocolate to the abstract satisfaction of a financial gain. It's far more nuanced than we often assume, hinting at why different joys feel, well, different.
But does the OFC cause the pleasure?
That's the crucial caveat. While OFC activity clearly encodes the subjective experience of pleasure or happiness, it's not yet clear whether orbitofrontal activity actually causes positive emotion or pleasure. Interestingly, patients with OFC damage still exhibit normal pleasure responses when they experience something pleasurable.
They still feel it.
They seem to, but they show impaired pleasure-related decision-making. This suggests its primary role is more about guiding behavior based on reward value, helping you choose what to pursue, rather than directly generating the feeling of pleasure itself. It's a sophisticated evaluator, not necessarily the sole generator of bliss.
Okay, so OFC evaluates. What else is lighting up?
Moving on, the anterior insula, AI, is another key player in our emotional landscape. This brain region is truly remarkable because it shows broad activation across a variety of emotional feelings, encompassing everything from maternal and romantic love, anger, fear, sadness, happiness, sexual arousal, disgust, aversion, unfairness, inequity, indignation, uncertainty, disbelief, trust, empathy, and beauty.
Wow, that's everything.
Pretty much. It's like a central hub for all kinds of feelings, providing a sense of our internal bodily state. Specific examples include activation when mothers viewed photos of their own children, or when subjects were seeing or making a smile, listening to happy voices, and even hearing pleasant music.
So it's involved in recognizing and feeling emotions generally.
It seems deeply involved. Most relevant to our discussion, selective activation of the left AI has been found when subjects were experiencing joy. This broad involvement suggests the AI is deeply integrated into our overall subjective emotional experience, providing a sort of conscious, what am I feeling right now? Filter for feelings, including joy.
The what am I feeling filter. I like that. And what about the front part of the brain?
Finally, we have the medial prefrontal cortex, MPFC, and the anterior cingulate cortex, ACC. These areas, located towards the front and center of your brain, are incredibly important in social cognition processes, which means how we understand ourselves and others.
Self-awareness and understanding others.
Exactly. This includes functions such as self-reflection, person perception, how we form impressions of others, and making inferences about others' thoughts. The medial frontal cortex isn't uniform. It has functionally distinct subregions. For example, the anterior dorsal cingulate sulcus is active when the link between an action and its outcome or reinforcement is critical, especially during error detection or when you're making a choice guided by the expectation of a reward.
Like learning from mistakes or anticipating good outcomes.
Precisely. In contrast, the ventral cingulate region activates during pain or during autonomic arousal, like when your heart races or you feel a pit in your stomach. Importantly, both regions are highly active during emotion and social interaction. Studies have observed ACC activation when subjects judge their own effective responses to scenes, which strongly suggests its role in self-knowledge of subjective feelings.
So understanding our own feelings.
Yes. This metacognitive awareness of our own emotional states, the ability to reflect on and understand what we're feeling, is absolutely essential for us to truly experience happy feelings as a subjective and personal reality. These three cortical areas, the OFC, AI, and MPFC-ACC, form a critical interconnected network in the cortical processing of pleasure and happiness.
That gives us a much clearer picture of the different brain regions involved, but that leads us back to our chemical conductors. So what does all this mean for the interplay between our two main characters, dopamine and serotonin?
The big question.
For a long time, there's been this big debate in neuroscience. Do they have opposing functions, or do they play complementary roles in reward and mood? It's like a central mystery in understanding our internal happiness systems. Does one cancel the other out, or do they somehow work together to create the feelings we experience?
It's a crucial question, and recent research has truly unveiled some fascinating and often surprising insights into their dynamic, sometimes paradoxical, relationship. One significant development in our understanding is the concept of co-release of neurotransmitters.
Co-release, meaning they're released together.
Exactly. We now know that neurons, the fundamental communication cells in your brain, often don't just release one chemical messenger. They can release more than one at the same time. This functional relevance of co-release is critical for truly interpreting their effects. It's like a finely tuned orchestra where instruments play different notes simultaneously to create a complex chord rather than just one note at a time.
Okay, so it's not just one chemical per neuron.
Not always, no. Let's look at the dorsal raphe nucleus, or DRN, which is a major source of serotonin in the brain. This DRN projects its fibers to the ventral tegmental area, or VTA, which is a key hub for dopamine production.
Serotonin source, talking to the dopamine source.
Right. This projection, surprisingly, is mainly glutamatergic, meaning it primarily uses glutamate, an excitatory neurotransmitter, but additionally contains 5-HT co-releasing neurons. This means some neurons in the DRN can release both serotonin and glutamate together, directly impacting the activity of dopamine neurons in the VTA.
Whoa, okay, so serotonin neurons can release other stuff too.
They can. And here's the crucial finding, and it's a game changer for how we think about happy chemicals. Research suggests that the additive effect of serotonin and DA, dopamine, conveys significant reward-related information and is subjectively highly euphorizing. Neither DA nor serotonin alone have such an effect.
Wait, say that again. Neither one alone causes euphoria. It's the combination.
That's what this research strongly suggests. It's a profound shift. It implies that true euphoria isn't about flooding your brain with a single happy chemical or relying on just dopamine for pleasure. Instead, it's about the sophisticated synergy, the precise integrated dance between dopamine and serotonin.
That completely changes the picture.
It really does. It challenges the simplistic more of X equals more happiness idea and reveals a much more elegant collaborative system at play, a conjoint increase in both signals. When scientists use a cutting-edge technique called optogenetic stimulation, which essentially allows them to control specific brain cells with pulses of light to directly activate DRN neurons.
Using light to trigger brain cells.
Yeah, pretty amazing stuff. They found it could be highly rewarding. But there was a key condition. This rewarding effect occurred only when glutamate was co-released alongside serotonin, or when glutamatergic neurons were specifically targeted. This led to vigorous self-stimulation by the animals and robust behavioral reinforcement because it effectively activated VTA dopamine neurons. So serotonin can contribute to reward, but often by nudging the dopamine system, often with glutamate's help.
So serotonin needs its friends to be rewarding.
In many cases, it seems so. However, the picture gets even more nuanced, even contradictory. When the stimulation was more 5-HT specific, meaning it primarily targeted neurons that only release serotonin without the accompanying glutamate, it often did not reproduce rewarding effects.
So just serotonin wasn't rewarding?
Often not. In some cases, it even led to behavioral slowing or aversion. This implies a fascinating point. Increasing 5-HT signals without a consecutive DA increase mimics aversive events.
That's wild. Increasing serotonin alone can feel bad.
It's counterintuitive, right? It suggests that a serotonin increase in isolation, without that critical dopamine component, can feel like a negative or undesirable experience. This is why just taking an SSRI, for example, doesn't automatically make someone feel euphoric. It's about rebalancing a complex system.
That explains a lot about antidepressant side effects, maybe.
Potentially, yes. The sources also highlight their distinct but complementary roles in reward prediction errors, PEs, which are how your brain learns.
Prediction errors, like when something is better or worse than expected.
Exactly. Think of it this way. The dopaminergic system codes reward prediction errors. It acts like a good or bad reviewer, signaling if something you experienced was better or worse than you expected it to be. For instance, if you get a bigger reward than anticipated, dopamine spikes. If it's smaller, it dips.
Dopamine is the better, worse signal.
Right. The serotonergic system mainly unsigned PE, meaning it signals general surprise or salience, whether positive or negative. It's like a general alert signal that simply flags, hey, something important just happened, pay attention. It doesn't necessarily tell you if it's good or bad, just that it's significant.
Serotonin is the pay attention signal.
Kind of. Therefore, their joint activity between both systems carries essential reward information, providing both the what and the is it good or bad. Serotonin also has a bivalent, meaning two-sided influence on motivation, impulse control, and even patience for future rewards, indicating its complex balancing act in how we pursue goals. And here's a significant detail. Tracing studies suggest that 5-HT is in a stronger position to control DA activity than vice versa, forming an intricately intertwined feedback loop where serotonin holds considerable sway over dopamine's activity.
So serotonin can boss dopamine around more easily.
It appears to have more influence in that direction, yes. It's truly a complex, dynamic dance, not a solo performance.
That's a profound shift in understanding. It's not just about what one chemical does in your brain, but how those neurochemical changes interact and ultimately feel subjectively. We just peeled back the layers on how the brain builds pleasure. But what happens when these powerful systems designed for well-being are hijacked?
Ah, the dark side.
Let's take this newfound understanding and confront a serious challenge. Addiction. Okay, let's unpack this further and connect our brain chemistry discussion to a real-world issue. How these systems influence addictive behaviors.
It truly does connect, and the links are incredibly intricate. The research points to what's called a diathesis, or a genetic or biological predisposition.
A vulnerability.
Exactly, where low levels of 5-HT serotonin are a known diathesis for the development of anxiety disorders, depression, but also drug addiction. This highlights serotonin's foundational role in emotional regulation and vulnerability. If your serotonin system is already underfunctioning, you might be more susceptible to developing these conditions.
So low serotonin could be a risk factor for addiction too.
It appears so. Furthermore, it's observed that most addictive drugs either cause increased 5-HT release or directly agonize 5-HT receptors. Think about common monoamine releasers like cocaine, amphetamine, and methylene-deoxymethamphetamine, MDMA, or ecstasy.
Right, they hit multiple systems.
They do. They all impact both dopamine and serotonin, but they do so in different ratios and with varying mechanisms. This is where it gets particularly surprising and counterintuitive based on the research.
Okay, surprise me.
The potency of drugs to release 5-HT negatively correlates with its potency as a behavioral reinforcer.
Negatively correlate. So more serotonin release means less reinforcing.
That's what it suggests. It suggests that the more a drug primarily releases serotonin, the less behaviorally reinforcing it is for an individual. For example, MDMA, which has a higher propensity for 5-HT release compared to other amphetamine derivatives like pure amphetamine, is self-administered, less than individuals with lower release of 5-HT.
So drugs that blast serotonin aren't as addictive, potentially.
It's complex, but that's the implication here regarding reinforcement. In simpler terms, if a drug heavily emphasizes serotonin release without a strong dopamine kick, it's less likely to be compulsively sought out. In fact, selective 5-HT releasers, drugs that only primarily release serotonin and don't significantly impact dopamine, are found to inhibit ICSS, which is intracranial self-stimulation.
That brain stimulation reward again.
Right, they inhibit it, and they are neither reinforcing nor experienced as pleasurable by humans.
So pure serotonin boosters aren't fun.
Apparently not. Consider specific examples. The compound M-chlorophenylpiperazine, MCPP, which primarily affects serotonin, was found to actively reduce positive mood and euphoria in studies.
It made people feel worse.
It seems so. And even acute intravenous administration of an SSRI, a selective serotonin reuptake inhibitor, a class of antidepressants, in healthy participants actually increased self-rated sadness and incompetence.
Giving an SSRI intravenously made healthy people feel sad.
In that acute setting, yes. This stands in stark contrast to the general perception of serotonin as a purely happy chemical. It suggests that simply elevating serotonin levels in isolation is not the recipe for pleasure or reinforcement. It can actually have the opposite effect.
Okay, my mind is a little blown right now.
It's definitely complex. Synthesizing this complex picture, the research indicates that 5-HT balances the behaviorally reinforcing effects of DA. It suggests that serotonin may be essential to inhibit reinforced behavior in order to promote behavioral flexibility.
So dopamine is the gas, and serotonin is maybe the brake, or at least the modulator.
That's a useful way to think about it. In essence, dopamine often drives the wanting and the intense reinforcement that underpins addiction. Serotonin, on the other hand, might provide the brake, or at least modulate that relentless drive, allowing us to adapt our behavior, to learn when to stop, rather than getting stuck in a compulsive, destructive loop. So while positive reward may be reflected by a combination of DA and 5-HT, that synergistic dance we discussed, punishment or the cessation of reward could be reflected by 5-HT in absence or reduction of DA.
Wow.
This dynamic explains why singular serotonin increases are inherently pleasurable and why their combined balanced action is so critical for the full spectrum of reward, motivation, and unfortunately, vulnerability to addiction. It highlights the delicate equilibrium within our brain's reward system.
That's a truly profound shift in understanding how addiction works, moving beyond a simplistic view of more of this, less of that. Now, let's zoom out a bit and look at the bigger picture. How does happiness itself change over a lifetime?
The long view.
Yeah, our sources suggest that happiness is dynamic by nature and is subject to cyclical or internal maturation processes. This brings up a really intriguing question for you and for all of us listening. Is happiness just a fixed, factory setting that we're born with, something predetermined by our genes and early experiences?
The nature versus nurture of joy.
Right. Or is it something that can actually be learnable and trainable throughout our lives, evolving as we do?
This question gets to the very heart of what happiness means for us individually and as a species. And the research offers a truly revolutionary model to answer it, the ABC model of happiness.
ABC. Okay, tell me about it.
This model proposes 3 neurobiologically distinct types of happiness, each predominant at different life stages and associated with different, though sometimes overlapping, brain systems. Let's dive into type A approach motivation, often described as wanting.
Okay, type A is wanting.
This is a kind of happiness characterized by desire and wanting, anticipation, pleasure, and ecstasy. Think of the intense highs, the thrilling pursuit of new experiences, the joy of achieving a goal.
Like youthful excitement.
Exactly. This type of happiness is particularly predominant in early or youthful times of life. It's momentary and more ephemeral, often described as ecstatic or linked to high moments and peak moments, short-lived and transient, but incredibly powerful. Neurobiologically, type A happiness is rooted in the powerful VTA-NAC pathway, the same mesolimbic dopamine system we discussed earlier, and is heavily driven by dopamine.
So early life happiness is very dopamine-driven, very wanting.
Largely, yes. This system is absolutely crucial for our survival and development. It's the engine that drives us to evolve, thrive, learn, explore the unknown. It's the engine of ambition, curiosity, and discovery.
Makes sense. What's type B?
Next, we move to type B avoidance motivation, or avoiding. This type of happiness is less about seeking intense pleasure and more about stress processing, escape, and relief. Essentially, the absence of unhappiness or threat.
So happiness as relief from bad stuff.
Exactly. This becomes accentuated in the middle-aged phase of life, often between the ages of 40 and 60, a time when people are often juggling careers, families, and significant responsibilities.
Midlife stress management.
You got it. It's functionally embedded in your body's stress system involving the amygdala, our alarm system, the hypothalamus, and the release of stress hormones like cortisol and adrenaline. The primary goal here is security and protection, actively working to avoid harm, manage risks, and maintain stability. When you successfully avoid a threat, overcome a challenge, or resolve a nagging problem, the resulting feeling is relief, which is described as a positive, low-arousal basic emotion.
That feeling of, phew, dodged that bullet.
Precisely. It's not the high of ecstasy, but the profound calm of safety, freedom from stress, and a sense of having things under control.
Okay, so A is wanting, B is avoiding. What's C?
Finally, we arrive at type C, assertion motivation, or non-wanting.
Non-wanting. Interesting.
This is the state of deep satisfaction, quiescence, and inner joy, often described simply as inner peace. This type of happiness is primarily attributed to older people, typically emerging and strengthening after midlife.
The happiness of later life.
Predominantly, yes. It's characterized by inaction, i.e. staying, acceptance, and a profound sense of contentedness with one's situation. What's particularly interesting here is that, unlike type A, it's not characterized by an involvement of dopamine.
No dopamine. So what drives it?
Instead, type C happiness is mediated by a completely different set of neurochemicals: endogenous opiates, your brain's natural painkillers and pleasure chemicals, oxytocin, our bonding hormone, acetylcholine, serotonin, and a different, more stable role than in type A, as well as endocannabinoid signaling.
A whole different cocktail of chemicals.
A very different one. It's a deep, stable form of contentment that doesn't rely on constant seeking, external validation, or high-octane thrills. It's a more integrated, profound sense of well-being that often comes with wisdom and acceptance.
ABC. Wanting, avoiding, non-wanting. That maps onto life stages.
It does, and this dynamic progression across the lifespan leads us to the concept of the U-curve of happiness.
I've heard of the U-curve. Happiness dips in middle age.
That's the one. This model shows how life satisfaction typically fluctuates during individuals' lifetime, taking the form of a U-curve with a dip in midlife, often between ages 40 and 50, and a significant rise in later years, peaking in old age. This counterintuitive finding leads to what social researchers and gerontologists have termed the satisfaction paradox.
The paradox.
The paradoxical finding that the elderly seem to be the happiest, despite often experiencing increasing physical complaints and the onset of chronic diseases. It seems illogical, right? Why would people facing more physical challenges report higher happiness?
It does seem weird on the surface.
Our neurobiological model offers a compelling rationale for this. As we age, our needs and desires are satisfied in a more cost-effective and efficient manner. We learn what truly matters, we become better at regulating our emotions, and we might simply become more adept at finding contentment in simpler things or within ourselves.
We get wiser, basically.
We simply get better and better at it over a lifetime, which signals a profound process of personal growth and flourishing. Life satisfaction only begins to decline a few years prior to death in what is termed the fourth age, indicating it's not simply about surviving longer, but about a genuine shift in well-being. Before this final stage, major depression is actually significantly less common among older than younger individuals.
So it's not just that unhappy people die younger. The survival bias.
The research effectively refutes common criticisms like the survival bias argument. Firstly, extensive studies show that happiness and health are not directly and linearly correlated, especially in old age where happiness emancipates from health measures. It becomes more independent of physical well-being. Secondly, the observed dip in midlife doesn't correlate with a surge in mortality at that age. Only a small fraction of people in Western societies die between 40 and 50.
Good point.
And thirdly, even after rigorous statistical scrutiny and application of large-scale mortality tables, the U-curve remains robust across 145 countries around the world, regardless of socioeconomic or political status. It's a truly global phenomenon.
Wow, 145 countries. That's strong evidence.
It really is. Adding another fascinating layer to this, research shows that empathy, our ability to understand and share the feelings of others, also follows a U-shaped course throughout the lifespan, with an increase in empathy being observed after the age of 40.
Empathy increases along with happiness in later life.
It parallels the rise in type C happiness, suggesting a broader socio-emotional maturation in later life. This entire model emphasizes that the software of happiness, how we experience and process it, what we seek and what satisfies us, is constantly and dynamically changeable and yet designable, rather than a fixed factory setting. It's an ongoing, lifelong process of maturation, from seeking outward thrills to finding deep, resilient inner peace.
That's incredibly empowering to hear. The idea that happiness isn't just something that happens to you, but something you can actively shape throughout your life, especially as you get older, is truly profound. So what does this all mean in practical terms for us, the listeners? Can we actually influence our brain chemistry and ultimately our happiness for the better? Can we actively train our brain for greater contentment?
Absolutely. The answer is a resounding yes. The research confirms that while some of our hardware, our genetic predisposition for certain neurochemical balances and brain structures, is innate.
Our starting point.
Right. But a significant part, up to 60%, of an individual's experience of happiness and life satisfaction can be attributed to a fundamental changeability in behavior or learning. This means our experiences are constantly updating our operating systems, reshaping how our brain processes emotions. Trauma, crisis, or simply the natural process of getting older, processing and learning from life experiences can indeed change the processes or set points in the reward system. Your brain is remarkably plastic, capable of adapting and reorganizing.
So we can change our happiness set point.
The evidence strongly suggests we can influence it significantly. A particularly powerful avenue for this kind of positive neurobiological influence comes from contemplative practices, such as mindfulness, meditation, or stress reduction programs.
Meditation and mindfulness really work on a brain level.
They absolutely do. These practices have been proven to influence the reward and motivation systems in the brain. They lead to measurable alterations in the limbic system, which is our emotional brain, including the amygdala, our fear center, the insular cortex, our body awareness hub, and the anterior cingulate cortex, involved in self-awareness and emotion regulation. Crucially, these practices also improve the connectivity between these areas, strengthening the communication pathways that underpin emotional balance and well-being. This isn't just anecdotal, it's demonstrating a clear neurobiological basis for how these practices can reshape our emotional landscape.
Better communication between emotional brain areas.
Exactly. It's no surprise then that these contemplative practices are strongly connected to the C state of happiness, that non-wanting state characterized by affiliation connectedness and altruism generosity, inner peace. Deep meditative states, in many ways, seem to embody this profound, stable C state.
So meditation helps cultivate that later life type of happiness.
It seems to be a powerful tool for doing just that. Beyond formal practices, other factors consistently supporting high life satisfaction include faith, the act of giving and letting go, cultivating love and loving relationships, or developing a deep dedication in relation to one's own actions and work.
Commitment, flow.
Exactly. This last point encompasses concepts like commitment, finding a state of flow where you're deeply immersed in an activity, and indeed practicing mindfulness in daily tasks. These aren't just feel-good concepts, they are actively shaping your brain's circuitry for lasting well-being.
And this affects health, too.
Definitely. The practical benefits extend beyond just feeling good in the moment. Healthy aging, as well as successful stress management, or a favorable way of dealing with life's challenges, not only seems to improve health in general and increase life expectancy, but it may be precisely these effects that can be increased through contemplative practice. The neuronal structures and specific neuroendocrine signaling pathways involved are demonstrably influenced by regular meditation. For example, consistent practice can lead to increased gray matter density in areas associated with emotion regulation, or even changes in the production of brain-derived neurotrophic factor, which supports neuron growth.
Wow, actual physical changes in the brain.
Tangible changes. In essence, by understanding and actively engaging with our brain's natural blueprint for bliss, we can cultivate a deeper, more lasting sense of contentment and even enhance our physical health and longevity throughout our lives. It's about consciously designing your own happiness.
What an incredible journey we've taken. We've truly plunged into the brain's blueprint for bliss. We started by exploring how happiness isn't just a fleeting emotion, but a complex, dynamic biological system.
A whole ecosystem inside us.
Right, with its own intricate chemical messengers like dopamine, serotonin, and oxytocin, specialized neural circuits in our hedonic hotspots, and a fascinating, evolving trajectory illustrated so clearly by the U-curve. We reinforce the critical distinction between liking and wanting, understanding how desire can be separate from genuine pleasure.
A crucial difference.
And uncover the collaborative yet nuanced relationship between dopamine and serotonin, particularly when it comes to reward and even the challenges of addiction.
That's surprising synergy.
Exactly.
Yeah.
So what a transformative idea, the U-curve and the satisfaction paradox, showing us that joy can truly deepen and evolve with age, becoming more profound and less dependent on external circumstances. It gives us all something truly positive to look forward to as we age.
It really does shift the perspective on aging. This raises an important question for all of us. Since it's simply not how our brain works to isolate the effect of just one chemical system, happiness is almost always mediated by a complex, integrated interplay of these systems. Perhaps our pursuit of happiness should focus less on singular fixes or quick highs.
Less chasing the dopamine hit.
Perhaps. Instead, we should consider how to holistically foster environments and practices that encourage the integrated, conjoint increase of our brain's natural reward signals. How might you, the listener, train your brain not just for momentary highs, but for a deeper, more lasting sense of contentment by understanding and actively working with your own biological blueprint?
Food for thought, working with our biology, not just trying to hack it.
Precisely. Thank you for joining us on this deep dive into the neurobiology of happiness.